Hello, good evening. My name is Pravalika, and welcome to week 3 of Sets Logic and Systems and Application. I hope my screen is visible. I'm sharing my screen right now. Okay, so a little bit about myself. Again, as I said, my name is Pravalika, and I'm a PhD student and a Prime Minister Research Fellow from the Indian Institute of Science. And before we begin the course, please don't feel like I'm nagging you with this same instructions over and again in every class. Okay, but this is mandatory instructions that I would like to give you. Okay, the first and foremost thing, this session is being recorded. And second, be respectful during the session, either in the chat box or anywhere else. Okay, and please put all your questions in the chat box here during the session. And in these sessions, I'll be discussing mostly the problem solving and MATLAB whenever it's required. Okay, and I'll be touching upon some theory, but I'm not going to go in depth for any theory. Okay, all the in-depth theory are from the main classes. So this is going to be only the problem solving session, right? So I didn't want to jump directly into problems. So what I do is I kind of give you some um, a little bit of theory first and then go into the problem so that it'll be like a fresh memory for you, right? So just jogging your memory up. And yeah, so for today, we'll be discussing union, intersection, and the difference. As apart from that, we'll be also discussing the properties of fuzzy sets, okay, and how they are different from classical set. All right. So with that, let's get started for today. So the first one I would like to talk about is union. Okay. So I hope you remember a Venn diagram, right? Let us say we have two sets. This is the whole universe. This whole box is the universe of disclosure. This circle is A, and let us say this is a set B. Right now, I'm talking about classical sets. Okay, so this is set A, this is set B. If I'm referring to something as a union between A and B, then I'm going to take everything that is in A and everything that is in B, right? That is going to be A union B. Right? For example, let us take a set where the values of x range from 1 to 3. Okay. So A is nothing but 1, 2, and 3, right? And B, the values of x range from 2 to 4. So that is equal to 2, 3, and 4. Okay. So in a classical set, when you're saying you are taking a union between two sets, then you are taking each and every element and combining them to form a new set. So in this case, if I'm saying we are combining A and B, then first let's write all the elements from A. It's 1, 2, 3, and let's look at B. We have 2, 3, and 4, but 2 and 3 are already there. So I'll leave it as it is and I'll add the extra element that is number 4, right? So now A union B is 1, 2, 3, and 4, right? This is how we do for a classical set, but it is completely different when we do it for a fuzzy set. So in a fuzzy set, let us say this is one membership function and this is another one, right? We have two sets here, fuzzy sets, set A and set B. And when I say we are taking a union in the fuzzy sets, then we are going to take the maximum membership function for a particular value of x. So at this point, this is the maximum. At this point, this is the maximum, right? So like that, we'll go on till here. And let us just say take this. In between this point is maximum. And for this value of x, we have two membership functions of a and b. Whichever is the maximum, we are going to take that, which is this, right? Again, from here, even though we have a as a continuation, The maximum value is for B, right? The membership function value is for B. So we go to B. Okay. So now it is some. This is for X, and this is the membership function. This is of A union B, right? So when you are taking a union for a classical set, you are basically getting all the elements together and you're putting it in a set. Whereas in fuzzy set, you are going to take the maximum value, maximum membership function value for that particular value of X. Okay. So let's try it out with an example. Okay. Here I have four X values, 1, 2, 3, and 4. Okay. And I have two fuzzy sets, and both of them have different membership values, right? So for X equal to 1, in fuzzy set A, we have 0.2, whereas in fuzzy set B, we have 0.9. So as I said, for A union B, we are taking maximum membership function value, right? So let us write it. Maximum of 0.2 comma 0.9 for 1 plus maximum of, for X equal to 2, we have 0.3 and 0.9. So let's take it, maximum of 0.3 and 0.9 for X equal to 2 plus maximum of 0.6 and 0.4 for X equal to 3 plus maximum of, here we have 0.6 and 0.5, right? So 0.6 comma 0.5 for X equal to 4, right? So let's look at it. So in between 0.2 and 0.9, the maximum value, oh, not visible. Is it visible now? I'm so sorry. Let's go back a bit. Okay. I'll start over again. Okay. So today we'll be looking at union, intersections, and difference. Apart, and after that we'll be also looking at properties of the fuzzy sets. All right. So in union, let us see how it is like when we talk about classical sets. We'll see how it is, how union properties apply, and whereas for fuzzy set, how union is applied. Okay, let us just see that. So in a classical set, let us say we have two two sets. Okay, set A and set B, where in set A, the X values lies in between 1 and 3, whereas in set B, the values of X lie in between 2 and 4. So if we were to write it in like a set, so A is equal to 1, 2, 3, and B is equal to 2, 3, 4, right? So let us talk about Venn diagrams. Okay, so in a Venn diagram, we'll just start over again. This part. Okay. Let us say this is our whole universe of disclosure, that is capital X, right? In that we have two sets, set A and set B. Now, when we are saying we want to take the union of A and B, we are going to combine all the elements that are in A as well as in B, right? So it is essentially going to look this way. So all the elements that are there in this green color or blue, actually it's blue, it's looking green. Okay, so all the elements which are in this particular area, so those all are nothing but a union between A and B. So if we were to write A and B together, Okay, so let us first write all the elements from A, right? It is 1, 2, and 3, right? Now let's go to B. We have 2, 3, and 4. So 2, 3 are already here. So let's just write 4. Okay, so this is the union when we are dealing with classical sets. But let's look at fuzzy sets. Okay, so the y-axis is our membership function value, whereas our x-axis is x values, right? So in a fuzzy set, when you are taking a union between fuzzy set A and fuzzy set B, what you're essentially going to do is you are going to take whatever the maximum membership function value is at that particular x value. So let us take at this particular x value, okay? The only membership function is here, but let us just take here, just call it x2. So here we have two membership function values, right? One from set A and one from set B. So which one you are going to take? You are essentially going to take whichever value is the maximum membership function. So which is going to be here. But let us look at it here, right? So set A value is set B membership value is here. So here the highest value is at fuzzy set B, right? So now if we were to take all the highest membership values in between both A and B for a union of fuzzy set A and B, then it is essentially going to look like this, right? Let's redraw it. Right? This is for A union B. Okay. So remember, for a union of two fuzzy sets, we always take the maximum membership function value for a given value of x. Okay. So this was the example that I'm saying. Okay. So let us take two fuzzy sets and the x values that we have are 1, 2, 3, and 4. Okay. So for x equal to 1, in fuzzy set A, we have the membership function value as 0.2, whereas in fuzzy set B, we have the membership function value as 0.9. So we'll write it as, we'll take the maximum between 0.2 and 0.9 for a given x equal to 1 plus maximum of, so for x equal to 2, we have two membership function values, that is 0.3 and 0.9. So we take the maximum between both of them plus maximum of 0.6 and 0.4 for x equal to 3 plus maximum of 0.6 and 0.5 for x equal to 4. Yeah, right? So now for x equal to 1, what is the maximum value here? In between 0.2 and 0.9. It is 0.9, right? So 0.9, 1 plus between zero point 0.3 and zero point 0.9, it's again 0.9 plus, and in between for x equal to 3, it is 0.6 plus for x equal to 4, it is 0.6, right? So this is A union B, where A and B are two fuzzy sets, right? I hope it's clear so far. Is it clear? Okay, thank you. Um, Okay, now let's look at intersection. So first we will discuss classical set again. Okay. So yeah, let us take a Venn diagram. Let's just have two sets, right? When I'm saying intersection, which means the whatever similar elements are there in A and in B. Okay, so the intersection between A and B is taken. So which is essentially going to be, this is too big. It's going to be this small part here. Right, this is A intersection B, this part. All right. Okay. So let us again take an example from the previous one. A equal to X such that 1 less than or equal to X less than or equal to 3. And B is such that okay, 2 less than or equal to X less than or equal to 4. Right? So if we were to write it as a set, A equal to 1, 2, and 3, B equal to 2, 3, and 4. Right? So the common elements in between A and B are these 2 and 3. Right? So A intersection B is equal to 2 and 3. Okay? So that is how we do intersection for a classical set. Right? So now let's look at fuzzy set. Let us take the same example as before. Okay, so let's call this as fuzzy set A. And this is your membership function values, and x-axis is x values, right? And let's take a triangular membership function here. And let's call this as B. Okay, so in union, we have taken the maximum membership function value. Whereas in intersection, it is going to be just the opposite of that. That is, you are going to take the minimum values. So now your for A intersection B, the membership function values are going to be this. Okay, so let's draw the graph again. It's only going to be this small part for A intersection B. Okay. So we'll take the same example as before. Let's take the same example as before and try to find the A intersection B. Okay. So let us write it as, so for A intersection B, we are taking the minimum value, right? So minimum of, for x equal to 1, we have the membership function values as 0.2 and 0.9. 0.2 and 0.9 for x equal to 1 plus minimum of 0.3 and 0.9 for 2, right? And then plus minimum of 0.6 and 0.4 for x equal to 3 plus minimum of 0.6 and 0.5 for x equal to 4. All right. So let's calculate it. So the minimum value in between 0.2 and 0.9 is 0.2 for x equal to 1 plus minimum between 0.3 and 0.9 is 0.3 for 2 plus in minimum value in between 0.6 and 0.4 is 0.4 for x equal to 3, and minimum value in between 0.6 and 0.5 is 0.5 for x equal to 4. So this is essentially going to be your A intersection B, right? It is completely different from what we have got from A union B. Right? So I hope you have understood the difference in between union and intersection and how to find them. Okay, please don't confuse between both of them, when to take minimum and when to take maximum. All right. So now let's look at difference. Let's again take a Venn diagram for a universe of disclosure capital X. Let's say we have A and B. All right. If I'm saying I want to know A difference B, that is, I want to know all the elements that are present in A, but I don't want the elements that are present in B. So which is going to be this part. Okay. But if I say the opposite, if I say B by A, that is, I want all the elements that are present in B, but I don't want the elements that are present in A. Okay, then it is going to be this small part. Okay, so this is a difference of in a classical set. Okay, coming to the fuzzy set, what you do is, so previously for a membership function value, we have taken one maximum or one minimum in between A and B and all of that, right? So now we are taking the minimum value in between mu of A and mu B bar. That is the opposite of mu B. That is 1 minus mu B, right? For a given value of some x. Okay. This is not required. Whereas for B by A, it is just the opposite. We take the minimum of mu A bar and mu B. Okay. So whichever is at the numerator, the same values you take. Whichever is at the denominator side, you basically take the opposite of it. Okay. So let's have a look at this one, the same question essentially. Okay. So before we go into this, what we'll do is we'll also write A bar and B bar. Let's write A bar, that is equal to A bar is nothing but 1 minus whatever membership function value we have at that particular x. So it is 0.8 by 1 plus 1 minus 0.3 is 0.7 by 2 plus 0.4 by 3 plus 0.4 by 4. And B bar is equal to 0.1 of 1, 0.1 for 2, and 0.6 for 3, and 0.5 for 4. All right. So now we have A by B. So we have A, we have B, we have A bar, we have B bar. We have all the values that are required for us. So when we are taking AB, what are we going to consider? We are going to consider A and B bar, right? So which is equal to minimum of, okay. So let's take the minimum of A, that is 0.2, and B bar, that is 0.1 for x equal to 1, plus minimum of 0.3 and 0.1 for x equal to 2, plus minimum of 0.6, 0.6 and 0.6 for x equal to 3 plus minimum of 0.6 and 0.5 for x equal to 4. Right? Let's write the values. 0.1 by 1 plus 0.1 by 2 plus for x equal to 3, both the values are same. So 0.6 and 0.6. So you'll just write it as 0.6 by 3 plus 0.5 by 4. So this is essentially your A given B. Okay. So let's find for B by A. So here what values you're going to take? You're going to take B and you're going to take A bar. Right? So let's take the minimum values in between both of them. So for x equal to 1, it's 0.9. For A bar, for x equal to 1 is 0.8 for x equal to 1 plus minimum of for x equal to 2 in between B and B bar are these two, right? 0.9 and 0.7 plus minimum of 0.4 and 0.4 for x equal to 3 and minimum of 0.5 and 0.4 and 0.4 for x equal to 4. All right. So the values are 0.8 for x equal to 1, 0.7 for x equal to 2, and 0.4 for x equal to 3, and 0.4 for x equal to 4. Right? So if you see A given B and B given A are entirely different. So they are not the same. Right? So these are the differences of fuzzy sets. Okay, the next ones that we are going to look at are properties. Okay. Let's take a quick 3 minute break. Again, we'll start back at 6:30. Okay. Okay. So let us resume. Okay. So We have multiple properties that were discussed in the class, which included law of contradiction, law of excluded middle, idempotency, involution, commutativity, associativity, distributivity, absorption of complements, and De Morgan's law. Right. So all of these properties were discussed during the class, but so these all are properties of a classical set. But fuzzy set does not follow three properties from the classical set. The three properties are law of contradiction, law of excluded middle, and absorption of complement. Okay, so let us look at what this law of contradiction is in terms of a classical set. So let us draw a Venn diagram. Let's just say we have a set, fuzzy set A, right? Sorry, not a classical set A. So this is the entire thing that it is in. Let us take the complement of A. So in a universe of disclosure X, if I'm saying I want A complement, so this is A and this is A complement, then it is going to be every other element which is not there in A, right? So which is this whole thing. Right? So now if I'm saying I want to take the intersection in between A and A bar, that is the complement of A, then what do we get? So when we are taking A, this circle, if we are taking A bar, apart from this circle, everything else, right? Is there anything common in between A and A bar? There is none, right? So here, in this case, the A intersection A bar is equal to null space. So there is no intersection or anything common in between both the sets whatsoever, right? So this law of contradiction is respected by a classical set. But when we take a fuzzy set, it is not going to respect the same thing. So let us see. Uh, let us take a triangular membership function. Okay. So this is A, right? So if I were to take a complement, this is the value 1. If I were to take a complement, right? The complement of A is nothing but 1 minus whatever membership function value at that point the fuzzy set has. Let's draw it in a different color. So for A, at this part, at this point, the membership function value is 0. So if I'm were to take a complement, then it is going to be 1. Similarly here as well, right? All these values are 1. Wherever the other membership function has value 0, it is going to have 1. So similarly, so this is going to be a complement, right? So now we have a complement. Now we want to know the intersection in between A and A complement of a fuzzy sets, right? So as we have discussed earlier, if we were to take intersection between two fuzzy sets, it is going to be the minimum membership function value, right? So here, let's look at it. It's all of this part, then this part, then this part, then this, this, right? It is basically forming this this shape in the graph, right? So it is definitely not null. So when at some values of x, we do definitely have some sort of membership function value, right? So it is not going to be a null set. Hence, the fuzzy set does not follow the property law of contradiction. Similarly, you can also try for law of excluded middle. That is, when you take A union A dash, I mean complement of A, then it is not going to give the whole universe of disclosure. So let us see in classical set. In a classical set, when you are taking A and the complement of A, and you are doing a union between both of them, that is, you're going to combine both the values, all the elements in the both the sets, then it is going to give you one whole box, right? So the whole thing, which is nothing but the universe of disclosure, capital X, right? So in a classical set, A union A bar is equal to X, whereas in A and fuzzy sets, it is not the same, right? So let's try with a different color. So when we are to take the union between two fuzzy sets, it's going to be the maximum membership function values. So this is essentially going to be your A union A dash in a fuzzy set. So which is not equal to your universe of disclosure, capital X, right? Hence, the second property is also not followed by a fuzzy set, but whereas a classical set follows it. And similarly, you can try it out for this as well. So in this, what you do is you take A dash and then you take B and you find the intersection between both of them first. And then you go, you also represent A, and then you try to take the union between the previous one and this one. Okay. In a classical set, you will get A union B, whereas in a fuzzy set, you will not get that. You will get a different one. So these are the three properties that a membership function does not follow. Okay. So for now, what we are going to do is we'll take two fuzzy sets A and B. Okay, and we try to find the other properties such as commutativity, associativity, distributivity, absorption, and the De Morgan's law. Okay. So far, any questions? I'll give you a minute time. So please drop a message in the chat box if you have any more questions in this particular thing. If someone is typing, I'll give up 2 minutes. Okay, you guys keep typing your questions. Meanwhile, I'll just write the questions. Okay. What happens when we take a difference of same fuzzy sets, right? I will show you. Okay, let us call this as A. Okay. Okay. And we'll draw A dash. Okay. This is A dash. Okay. And let's draw B. Okay. For now, since we have already drawn this, I don't want to make it more clumsy. So let's just find B by A. That is, you're taking B difference A, right? So now you are going to find the minimum values in between B and A bar. Right? For this one, you take B and A bar. Okay. So let us see. At this point, at the starting X values, so these are the minimum membership function values, right? And even when we go for B, these are the lowest. And then this, right? So this is the difference. I hope I have answered your question, Yamuna. Or did you mean if you are taking the same fuzzy sets, like A and B being the same ones, then you will get a null set. Let's try that as well. Okay. So this is A bar and this is A, the red one. If we were to take the minimum values till this point, A bar is giving us the least values, right? Oh, we are not getting null, sorry. And then we have this part, right? And then it goes this way. Okay, if we are going to take the same A and A bar, and if you want to like find the difference between both of them. Okay, still there is some membership function values which is left. So it's not going to be a null value. Okay. By the curve, by uh, Nehashish, so for now, we'll just stick to whatever content is there for this week. Okay. At the end of the class, I will answer your question. Okay. For the Bell membership function. Yes, yes, we won't get the null set. But if actually it depends on what the graph structure is. Okay. So there might be some cases where you might get null set, but in the example that I have taken just now, in this one, it is not a null set, as you can see in the graph itself. Okay. Okay. Let's go ahead with our problem. So I have a universe of disclosure, capital X is equal to 1, 2, 3, 4, and 5. Okay. So I have 5 X values, and let us take two fuzzy sets. Okay. Set A is equal to 0.2 by 1 plus 0.5 by 2 plus 0.8 by 3 plus 1.0 by 4 plus 0.6 by 5. Okay, please note it down simultaneously. Okay, again, I'll not come back for the same question. 0.4 by 1 plus 0.7 by 2 plus 0.3 by 3 plus 0.9 by 4 plus 0.5 by 5. Okay, so we have the universe of disclosure with 5 elements 1, 2, 3, 4, and 5. And we have two fuzzy sets, okay, with 5 elements each, and each one having its own membership function value, right? So the first one that we are going to look at is commutativity. Okay, which is essentially saying that A union B is equal to B union A. Okay, right. Let's try to find A union B, which is nothing but maximum in between 0.2 and 0.4 for 1 plus the similar. You take the maximum values of all the membership function values which are present in between both the sets. Okay, let's write it down directly. In between 0.2 and 0.4, 0.4 for x equal to 1. In between 0.5 and 0.7, 0.7 for x equal to 2. Plus in between 0.8 and 0.3, it's 0.8 for x equal to 3. And then 1 for x equal to 4. And 0.6 for x equal to 5. Right? So this is your A union B. For B union A also, you are basically taking the maximum, the maximum membership function value in between A union B, right? So again, it is going to be the same. Right? So, which basically proves that a fuzzy set follows the property commutativity. That is A union B is equal to B union A. Is it clear so far? Okay. Okay. Now let's go ahead with another the other one. Oh, and there is one more as well. So in commutativity, this is one. Another one is A intersection B is equal to B intersection A. Okay. So let's just find out that as well. A intersection B. Okay. So per intersection, we take the minimum membership function value, right? So in between A and B, 0.2 and 0.4, the minimum value is 0.2, right? 0.2, 1 plus 0.5 of 2 plus 0.3 of 3 plus 0.9 of 4 plus 0.5 of 5. So for B intersection A also, we are taking the minimum in between, again, the same values, 0.2 and 0.4 for x equal to 1, right? So for similarly for all other elements as well. So which is going to give us the same values. Okay, so which basically concludes that fuzzy sets follow commutativity property. Okay, right. So the next property that we have is associativity. Okay, associativity is nothing but A union B union C is also is equal to A union B union C. Okay. So if you keep your brackets here or either in between the second and the third element, it is essentially going to give you the same output. Okay. So let's define C as well. So let's take C 0.1 for x equal to 1, 0.6 for x equal to 2, 0.4 for x equal to 3, plus 0.8 for x equal to 4, and 0.7 for x equal to 5. Okay, so we need A and B values also, right? So let's bring our A and B values. Okay, so let's first calculate the LHS, the left hand side. Let's calculate LHS. LHS is nothing but A union B union C. Okay, so first let's get A union B. We already have A union B here, so I'm simply bringing it down. Right, this is our A union B. And we have our C value also here, right? Hmm. Now let us take the union in between both of these fuzzy sets. So A union B union C is equal to. So union means you are going to take the maximum membership function value. So 0.4 by 1 plus 0.7 for x equal to 2 plus 0.8 for x equal to 3 plus 1 for x equal to 4 and 0.7 for x equal to 5. Right? So now we have solved for the LHS side, that is the left hand side. So now let us look at the right hand side. So what is there at the right hand side? A union B union C. Okay, so for this we need to find A union C first. Sorry, B union C first. Let us look at B and C together. So these two, right? For x equal to 1, the highest is 0.4 plus for x equal to 2, the highest is 0.7. For x equal to 3, the highest in between those is 0.4. For x equal to 4, it is 0.9 and 0.7 for x equal to 5. Right? Okay. Now we also have A. Let us bring A here. So let us solve for A union B union C. For x equal to 1, the highest value is 0.4 plus for x equal to 2, highest is 0.7. For 3, it is 0.8. For 4, it is 1. For 5, it is 7. Right? So shall we look at both of LHS and RHS side? 0.4, 0.7, 0.8, 1 and 0.7. So we can say LHS is equal to RHS. Right? LHS is equal to RHS for us. So which means that the fuzzy set is respecting the associativity property. Right? Clear so far? So the third property that we are going to look at is idempotency. That is A union A is going to give you A and A intersection A is going to give you A. Okay. Let us take A. Okay. So even if we write A union A, if we are to take um, with respect to intersection, okay, I'll do that as well. A intersection B intersection C is equal to A intersection B intersection C. Okay, so this is for intersection. This is for union. So even if you solve for this, it is essentially going to give you the same output. Okay, you can try it on your own. But in case if you are facing any issues, like if you were not getting LHS is equal to RHS, just let me know. after the session ends, I'll wait for some more time. And if you're not getting the same output, just let me know and we'll do it together. Okay. Okay. So A union A. So when we are taking the minimum or the maximum in between same values, that is 0.2, zero point 0.2 and 0.3, 0.3, it is going to give you the same output, right? 0.2 or zero point 0.3, whichever question it is. So when we are taking maximum in between 0.2 and 0.2, it is 0.2 of 1, 0.5 by 2, 0.8 by 3, 1, 4, 6 by 5. And A intersection A is also going to be the same. So there is no minimum, no maximum in between the same numbers. For equal numbers, there is no minimum and maximum. So it is going to give you the same values as output. So this property is also followed by a fuzzy set. Right? So far we have seen three properties: commutativity, associativity, and idempotency. Okay. The next one, let me look at the slides. Involution, which is A double bar is equal to A. Okay. So A bar means complement of A. A double bar means again you take the complement of A bar. So it is basically like this. So where this tilde is a complement. Okay. So when you are taking complementary over complementary, it is going to bring back to the same value. Okay. Let's do it with that same example. We have A. Let's find A bar, that is 1 minus whatever membership function value we are having. 0.8 by 1 plus 0.5 by 2 plus 0.2 by 3 plus this is 0 by 4 plus this is 0.4 by 5. Please let me know if I'm going fast at any point. Okay, I will repeat the same thing again. Okay. I try to keep it as slow as possible so that everyone will understand. But in case if you are not following it at any point, just stop me there itself. Okay. The chat box is right in front of me. I'll immediately see. Okay. Now, if I'm saying we are taking A double bar, that is you are taking the complement over A bar, right? So 1 minus 0 0.8, 0.2, 6.5, 1 minus 0 0.8 is 0.8, 1 minus 0 is 1, and 1 minus 0 0.4 is this, right? So this is nothing but A only, right? A double bar is equal to A. So a fuzzy set also follows the property of involution, right? Okay. And then we have absorption. So absorption is A union A intersection B is equal to A, and A intersection A union B is equal to A. Let us see how it is in a classical set. Before we go into fuzzy set, just look at classical sets. Okay, this is A, this is B for us. First, let us see A intersection B. A intersection B is this area, right? This area union with A. So A is going to be, sorry. So sorry. Okay. A is going to be this whole thing. Okay, this is going to be this whole thing. Okay, so this small part and this whole part intersection is nothing but A, right? So in a classical set, this is how this works. So the same thing is for the second part also. Okay, so let us try the same thing for A and B. I am going to solve the first one. Okay, let us take A intersection B. Did we do A intersection B? Yeah. So we have A intersection B here. Okay. So now we want to take A union, sorry, A union, A intersection B. So the union between this and this fuzzy sets. Let's calculate it for A union, A intersection B. That is, we take the maximum values, right? Maximum is 0.2 plus 0.5 by 3 plus maximum in between 0.8 and 0.3 is 0.8 plus maximum between 1 and 0.9 is 1 plus 0.6 by 5, which is nothing but A, right? So fuzzy sets uh, follow the property absorption as well, just like a classical set. Clear so far? So the last one that we are going to see is a De Morgan's law. That is A union B whole bar is equal to A bar intersection B bar. Okay. So do you guys want to do it or should I do it? Like, I'll give you some time. You guys can do it. And after some time, I will do it. Is that okay with you? Or should I just do it off? Okay, I'll do it. Uh, okay, let's take A union B first. We have copied it, right? It's intersection. Let us take A. Okay, this. Let us take A union B. And A union B whole bar is equal to nothing but the complement of A union B. This 0.6 by 1 plus 0.3 by 2 plus 0.2 by 3 plus 0 by 4 plus 0.4 by 5. Right? Okay. Let's take our A and B's and let's also find A bar and B bar. Okay. Let's find A bar. 0.8 by 1 plus 0.5 by 2 plus 0.2 by 3 plus 0 by 4 plus 0.4 by 5. For B bar, 0.6 by 1 plus 0.3 by 2 plus 0.7 by 3 plus zero point 0.1 by 4 plus zero point 0.5 by 5. Now we are going to take the intersection between A bar and B bar. So that is the minimum values we are going to take. 0.6 by 1 plus 0.3 by 2 plus 0.2 by 3 plus 0 by 4 plus zero point 0.4 by 5. Okay. So now we know A union B whole bar and we know A bar intersection B bar, right? So aren't both of them same? They are the same, right? So hence our fuzzy set also follows the property of the De Morgan's law, right? So this is one De Morgan law. The other one is A intersection B whole bar is equal to A bar union B bar. Okay, you can try out the second one by yourself. Okay, so this is about the De Morgan's law. Okay, I'll give you some time. Please do the De Morgan second part. I'll give you some time. I'll keep it as it is. Let's take time till 7:10, and if just let me know as soon as you get to know it. Okay, I'll wait for some time. Okay, I hope you guys were able to solve for the second De Morgan's law. Right. So with this, I'm practically done with whatever I have prepared. right? So from this week's class, what I would suggest you all is to remember what properties that a fuzzy set do not follow, and how to calculate the union between two fuzzy sets, how to calculate the intersection between two fuzzy sets, and how to calculate the difference between the two fuzzy sets. These are kind of important for you, especially when you want to attempt your exam and everything. Okay, so kind of have a grip on the properties and the other three. Okay, so with that, I'm basically done for today's class. Okay, if you have any questions from this week's content, just let me know. I'll help you out. Uh, if there are no questions, one question was asked on Bell membership function. I'll proceed to answer that. So I'll just give you a minute or two so that if anyone has any questions from this week's content, just let me know. Okay, if there are no questions from this week's class, thank you so much for joining. I'm done with the content part, but I will be online till 8 p.m. Okay, so you can ask any questions and I'll be happy to answer. Okay, thank you guys so much for joining. And now I'll just proceed with the question that was asked by Snehashish. So, why the curve widens in Bell membership function if B parameter is decreased? Uh, okay, so just correct me if I'm wrong. Just correct me if I'm wrong with this membership function. Okay, it's 1 by 1 plus x minus c by a whole power b. I believe this is the membership function. Uh, Snehashish, just help me out here. I hope this is the right one. I'm really bad with formulas and all of that at some points. Okay, so all the three variables here, A, B, C, all the three parameters has different reasons to be there. Okay, so C is basically the center. Okay, so if you see this whole membership function, B is basically defining the steepness of your curve. That is how fast your curve is going to fall or how fast it is going to decrease from the center. From this point to this point, how fast is it going to decrease? So if I have a center here, is it going to decrease like this or immediately or too fast? Okay, slow, medium, and the fastest. Okay, so this is basically defined by the parameter B. Let us take an example. Okay, let us just take A equal to 1. So that we'll just get it out of our system. And let us take B equal to 5. 1 by 1 plus x minus c power 5. Okay. So this is 1. Uh, let us take if b is equal to 10, it is going to be 1 by 1 plus x minus c whole power 10. Right? So when we are taking, how do you say this one? Okay. If we are taking b value as a greater value, then the curve is going to fall faster. Yeah. Or let's just take x minus c as some 2 or something. Okay, and just put the values there and try. If this is c, when the value of b is greater, then it is going to fall faster. Sorry. Yeah. When b is greater. is very large. Okay, it is going to fall fast. If B is small, sorry, B is small, it is going to take some time to fall down. Okay, you keep trying different values of x minus c, and you keep decreasing, keep different values there, maybe 2, 3, 4, 5, and all of that for fixed values of b equal to 5 and b equal to 10. Okay, just have some data points. Try to just plot it in Excel or something and try to see the difference in between B and C, and in between B equal to 5 and B equal to 10. Okay, so that is when you'll understand why it is falling faster and why it is falling slower. Okay, okay, you have done it in MATLAB. Okay, that's really good. Uh, yes, as you decrease B, it is going to fall slower. That's what I was saying. Right? So it will take some time to fall down if you are taking B as less. If you are taking B as higher value, then it is going to fall immediately. So it will be like this. So this is for B small. The inside one is for B large. So this power, exponential power, is in the denominator, not in the numerator. If it is in the numerator, then the opposite will happen. Since this whole thing is in the denominator, the value keeps this value keeps on increasing, which means the membership function will keep decreasing. Right? It's in the denominator, not the numerator. What you have got is right. So just remember, for smaller value of B, the transition happens slower. If the value of B is large, the transition happens fast. Okay, there will be a sudden drop immediately, right? Because the denominator will increase by so much, the whole thing will decrease faster. So immediate drop will be there for B, if for greater B. Okay. Thank you so much, Snehashish. Thank you everyone for joining. So if you have any more questions, I'll be available till 8 p.m. Right here. So do ask me questions if there are any. If not, we are done for today. Thank you so much. What distance matrix is generally used for dissimilarity measure between two fuzzy sets? So there are different types of distance measurements, uh, Snehashish. So one is Hamming distance. That is, you take the difference between the membership functions of a given x value. Okay, and you take the absolute between both of them, and you sum all of them up. Okay, for multiple values. So for x equal to 1, x equal to 2, x equal to 3, whatever difference is there between the membership values, you take all the absolute difference and then you sum all of them up. That is for Hamming distance. And other one is you can use a Euclidean distance. That is, you take the difference between both, and then you square it up. Okay, and then you take the sum of all and then you put a square root over it. Okay, so these are the some of the types of distances, but you can do other things also.